as shown in the schematic, the surface temperature of a steel wall and temperature of water flowing over the wall are given. The thermal conductivity of steel at the mean temperature of 70 is 61.7, and the thermal conductivity of water at the mean temperature of 32.5 is 0.62. Determine the convection coefficient and temperature gradient in wall and in water at wall surface. So you're asking us to determine H, temperature gradient, that will be how temperature varies, right, with the distance for the wall, and dt dx for water at wall. Okay, so let's start with this question is easy to solve mathematically. It's complicated in terms of the insights we need to follow. Well, first thing to note is that they're giving us the thermal conductivity for steel as a constant, so we can use a single value for the whole thing, which is convenient. And also they're giving us the conductivity for water, right? So they're giving us K for water, and that is 0.62. So note this is K for water, not H for water. So it's not taking into account convection, right? This is only conduction. All right. Now the easiest one to do is this one here. We can start with it if we want, because check out delta T dt dx. In this case, our dt and x are defined. So in this case, it will be the equivalent of this, and that will be 100 minus 40, 40 minus 100 over 0.35. Right, that's going to give us 171.4 Celsius or Kelvin per meters. Okay, and that will be the first. You could have that as your answer. Now the only thing to note is that because heat is traveling on this direction here, and our gradient is 40 and 100, so that will be backwards, right? It will be 40 minus 100, so equivalently it will be 40 minus 100 divided by 0.35, which would be the same value, just negative, to show you that that is a negative gradient. What does that mean? Well, think about it. If we have temperature on one side and x on the other one, and we're looking how one varies with the other, we're going to have 100 over here and then 40 down here. And then we can have, for instance, the bottom of the wall here and the top of the wall over here. Right, so top of the wall with 40 and bottom of the wall with 100. So we're going to have something like that. Right, varies linearly, like so. And note that this guy is decreasing, temperature is decreasing as x increases. Right, so our dt dx is smaller than 0, it's negative. Okay, where does that show up in Fourier's law? Well, it shows up on that negative sign there that we remove so long as we make this the largest number minus a smaller number, right? Because what is going to happen every single time is that this number here should be negative, right? Because it's going to be in this case 40 minus 100. So this negative, they go away. But because students generally get very confused with this, I say always keep this number as positive, the one that's greater minus one is smaller, so you can lose this one here and avoid mistakes. Okay, but in this case here, the gradient has to be negative because it's decreasing. All right. So if you're looking for Q's and stuff, you can always ignore the negative. If you're looking for the gradient, watch out. Okay, it's not incorrect to say positive 171.4 Celsius per meters or Kelvin per meters, as long as you show the gradient decreasing, or or you explain somehow that gradient like we did here on this graph. Okay. Okay, so that's part one. That's one of the answers. Now the next one is looking for the convective coefficient and the TdX of water. Now this is where it gets a bit more interesting. because, check it out, on the previous videos, you can look at the previous videos, the one that we determined that actually the Nusselt number is the equivalent of a non-dimensional gradient, right? And we talked about how in that example, as y goes to 0, that's where we can determine our convective coefficient, right? We talked about that. And we also said that as y goes to 0, our Q for conduction equals our Q for convection. The reason for that is, remember that if we zoom in all the way until we're looking at the two layers, the atoms of steel touching the atoms of water, the way that heat is going to be exchanged is actually due to the conduction, because the molecules of one need to vibrate and send that energy to the molecules that are next to it, touching it. So in this case here, our y is given as x. Let's look here, over here on the corner here. Right? So as x goes to 0, as this guy goes to 0, we're going to the wall surface. Okay, so that will be the equivalent of the previous one, our y on the previous problem. So that means that two things, right? The thing that we're looking for, we can determine as y goes to 0, and that the conductivity and the convection are the same. What are these guys here? Well, we know conduction is given by Fourier's law, and then we can have the negative or not have the negative. It's going to be up to you, because the negative is going to show up on both these equations. That's Fourier's law just there. And the one for convection, we know it obeys Newton's law of cooling. There's another negative there. So whether you want to keep them or not keep them, that's not going to matter, because they're going to go away anyhow. If to make the two of them equal, that means that minus k a dt dx equals minus h a dt, right? And then the areas, as you can see from our drawing, the area are the same, and kind of by definition they're the same, right? Because we're talking about the same region. So these guys go away, and that's why, by the way, it's given in heat flux, not in just big Q there. We don't need these guys either. And then we can see that our H will be related to our delta T's and our dt dx, right? So the gradient on the conductive side, so Q gradient on the conductive side, which we know already, equals H and dt on the convective side. What is the dt on the convective side? Well, it's between the wall and the fluid, right? Where's our fluid? There's here 25, so 40 and 25. So that means we can find our H at x tends to 0 by doing H will be, okay, that's 61.7 watts meters Kelvin, or Celsius for that matter. dt dx, which we found to be 171.4, and that'll be Kelvin per meters, and then the divided by dt on the convective side, which is 40 minus 25. Now, if you guys want to keep the negatives throughout this whole thing, then obviously there will be a negative here, but then this guy also will be negative, because it will be 25 minus 40, right? So the negatives will go away as well. That's where the negatives end up showing up. So up to you guys how you want to think, whatever rocks your boat. This is also Kelvin or Celsius, right? So hopefully we'll get rid of stuff. So Kelvin and Kelvin, and that's it, right? So we're going to have the unit for convective coefficients. This turns out to be, what did I get? 705.14 watts per square Kelvin. So that will be our answer for what is H, right? And then lastly, we can find what is the last part, which is, what is the last part is asking us, what is the dt dx for water, right? And what we're going to do is precisely the same thing. Like we can do, again, the same idea, do a little energy balance on the surface here. That's what we've been doing so far. Do a little energy balance on the surface here, and then we can know that all the energy that's going into the water is coming from the wall. So therefore, that's why we can also say that convective and conductive are the same at that point there, right? Because we know Q that's coming through this guy here is due to conduction, and then Q that's going to go to water is due to convection. And right on the surface there, if we can zoom in even further, we're going to be looking just at this part here, right? And we can see all the energy that goes into the water there is coming from this wall here. So therefore Q equals Q, conduction and convection. Okay, so it's the same thing we did here. We're going to do, let's do it one more time. So K A dt dx equals H A dt. Okay, once again, we can get rid of this, and the negatives. All right, but now if we're looking for the one at the water, right? So if we're looking for only for this, it's only for water. Then the dt is not the same anymore, right? This dt is not the same anymore, right? Because this dt now is the gradient. This gradient here is a gradient for water. In our water, let's look at what we have for water. Let's draw the wall once again, just bigger this time. So this is my wall, and then we have water here on top, right? And what do we have there? We have 25 on the outside, and we have 40 right there on the surface. So my gradient is going to be, what is the difference in temperature from this 40 to this 25 on this very, very small space that is x tending to 0, right? And you can see, like beforehand, you can see that as x goes to 0 on a dt dx, as my x is going to 0, there my dt dx should be tending towards infinity. So we should expect a very large number here, right? If we want to find dt dx using this equation, that means that my dt dx for my water equals, just continue on that equation, h over k delta t or dt, right? We know all these things, and now the only thing that is going to change from our previous equation is that now we're not really interested on the conductivity of the steel, right? Because we're looking only at the conductivity of water. We want to know on that water barrier there, when we're going from that 40 there from the water to that 25 on the water, right? Both things in the water, then what is our dt dx? And this will be 705 over 14. The K for water was given as 0.62, and my dt for water is 25. And then once again, this is the last part in which this guy would be negative and will give you a negative gradient, right? So up to you, all you want to think of it. The gradient is always going to be negative. So therefore, if you guys remember that and you know it's from hot to cold, then you can ignore the sign and just put it by the end if you wish. Unit-wise, we have this, and we have this, and then we're multiplying by Kelvin or Celsius. Okay, so watts and watts, Kelvin and Kelvin, meters and square, so Kelvin per meter or Celsius per meter will be our gradient. And this turns out to be a very big number, approximately it's 75059.83 something, so we can approximate that to, let's just go with 60, all right, Kelvin or Celsius per meters. Now, this is a gradient. Once again, let's look at the graph. So that's going to be, I have t here and x here, and then at x, as my x goes away further, then I'm going to have my t of 25, and where my x is 0, I'm going to have my t of 40. So once again, my gradient is downwards, right? Downwards like so. Once again, my dt dx is negative, right? So my actual answer is dt dx at wall for water equals minus 17,060 Celsius or Kelvin per meters. Okay, if you guys give me positive numbers, I will consider it, but I want you guys to be sure of the reason why the negatives occur in these problems. All right, questions, hit me up.